Hello guys, and welcome back to my channel. Today we'll be doing a sequel to a video that I did last week about complex numbers, and that video was about the Cartesian forms, and today we'll be going over the polar and exponential forms, as they're also common questions in the IB exams about complex numbers. So if you haven't watched my last video, I suggest you watch it before coming into this one, or that you at least know Cartesian complex numbers to a moderately good degree. So last time we talked about the complex plane. In the complex plane we can break down a Cartesian complex number into its two components, the real part and the imaginary part. And the imaginary part will be our vertical direction, and the real part is our horizontal. And so in this case 1 plus 3i is a 1 unit shift to the right and 3 units upwards, and our complex number z will be right there on the complex plane. And our modulus of z, or the absolute value of z, will be the distance from the origin to that complex number. In this case it's at the square root of 10, because it's the square root of the real part squared and the coefficient of the I of the imaginary part squared. So this is the Cartesian way of representing a complex number. Now the polar form is similar to how you would represent coordinates in a unit circle. That's why I have it here. However, a unit circle is in a real xy plane. Here we have our vertical axis is imaginary, so we have to put an I behind every time we have a sign. And so basically what is happening here is an angle will be formed between the modulus of z and the real axis, and this angle will allow us to get the vertical and the horizontal components, or the imaginary and the real components of the complex number, in terms of sine and cosine and the absolute value, because we're going to have to scale it. So in a unit circle you wouldn't have to scale anything because the radius is 1. In this case it isn't, so we're going to have to multiply this. So the vertical will be the modulus of z times sine of theta. From trigonometry you should be quite familiar with this. And the horizontal is the absolute value of z times the cosine of theta. And hence we can factor out the absolute value of z and add these up to represent our complex number z as r, or the absolute value of z, times cosine theta plus I sine theta. So basically that's all of this part. And there was this French guy, I'm not going to try and pronounce his name because I'm going to butcher it. He came up with a theorem, and it'll make more sense once we talk about exponential forms, or Euler's way of representing complex numbers. But the formula is, if you want to raise a complex number to a power, a real power, then what you can do is raise the polar form, the absolute value, to that power, and you can multiply the angle that you input into the cosine and the sine by that power. And similarly, if you want to multiply two complex numbers, then you can multiply the absolute values, or the moduluses of each one, and then you can add up the angles and overall represent it like this. Whereas in Cartesian form you would have to expand, and that can take a lot of time with high powers, or it would even be impossible if you had a square root as a power, or like a fraction as a power, I guess. So like z to the 1/2, or the square root of z, you wouldn't be able to do with the Cartesian form. And we'll be moving on to some IB style questions, but before that we'll do a quick check of understanding. And this video is dedicated to my friends Timmy and Serafina. They wanted a shout out, even though not many people watch these videos. But yeah, let's move on to some questions. So our first question is relatively simple. It's just applying the DMT theorem, or the DM theorem. And we want to represent this in Cartesian form, and it's z is equal to cosine of pi over 6 plus I sine of pi over 6. And we want to raise it to the fourth power. So to do that, as we've just seen, what we can do is multiply each of the angles by 4. And in this case, we don't have to do anything with the modulus because it's 1 raised to the 4 is still 1. So z to the 4 is going to become cosine of 4 pi over 6 is 2 pi over 3. So 2 pi over 3 plus I sine 2 pi over 3. And we want to represent this in Cartesian form, so we're actually going to have to get the values for cosine and sine. So cosine 2 pi over 3 is, if we draw the graph of cosine, then we can see that this is pi, this is pi over 2, this is pi over 3, and that would be, so pi over 3 is pi over 3 away from 0. And so if we go pi over 3 away from pi, which would be 2 pi over 3, these should have the same values except opposite signs because of this axis of reflection here, but it would be negative, so negative axis of reflection. So cosine of pi over 3, cosine of 60 is just 1/2, right? So this would be negative 1/2. So negative 1/2 plus, and we can do the same with sine. So this is our pi over 2, pi over 3, and 2 pi over 3. We can take our value at pi over 3, it's going to be the same thing as 2 pi over 3, because we have now a positive axis of reflection, so the value doesn't change. So sine of pi over 3, of course, root 3 over 2, so this is going to be root 3 I divided by 2, and this is z to the 4th in Cartesian form. So pretty simple question. Let's move on to something a little bit more challenging. For this question, we're supposed to find the cube root of this complex number. I'm going to give you some time to pause, have a go at it, and be moving on now. So to find the cube root of this number, we can say that z is equal to 8 cosine pi over 2 plus I sine pi over 2. And we can use the same theorem to say that we can take the modulus, raise it to the 1/3, and we can take each power, each angle and divide it by 3, or multiply it by 1/3. So this is going to equal 2, and then cosine pi over 6 plus I sine pi over 6. And we want to represent that in Cartesian form, which I forgot to mention, but this would be 2 times cosine of pi over 6 is root 3 over 2 plus I times 1/2. So the 2's here will cancel, and we're left with z to the 1/3 is equal to root 3 plus I. Pretty cool. Let's move on to an IB style question. Okay, so for this question is given that z cubed equals 1. We're supposed to find all of the possible values of z. And immediately you might think 1. And while technically correct, that wouldn't be all of the solutions. So what we have to do is we would have to represent z as a complex number, because also keep in mind, anything cubed or anything to the power of n will have n solutions, but some of those solutions might be complex. So keep in mind, if you have like z squared equals 2, you know that's going to have 2 solutions and both of those are going to be real. But if you have z cubed equals a number, then you're likely going to have 2, actually I think it's always going to have 2 imaginary or complex solutions. So if you want to pause the video and have a go at this. I'll be moving on shortly. Okay, moving on, so we have z is equal to, well, 1 is on the real axis, so the angle formed is going to be 0. However, 0 is the same as 2 pi. It's the same as 4 pi in terms of angles. So we're going to say this is cosine of 0 plus 2 pi k plus I sine 0 plus 2 pi k. And now, oh sorry, this is z cubed. And we want to find z. So this is going to be cosine of 2 pi over 3 k plus I sine 2 pi over 3 k. Okay, now we can put also k is an integer. Right? K is values like 0, 1, 2, 3, 4. And now we can find our values by just putting values for z, for k. So let's say k equals 0. Well, k equals 0, we're going to have cosine of 0 plus I sine of 0, which is going to give our solution, our first solution, of 1. If we put k equals 1, and what's going to happen is we're going to get cosine of 2 pi over 3 plus I sine 2 pi over 3. And cosine of 2 pi over 3, as we've had before, is negative 1/2 plus I sine of, plus I times root 3 over 2. And if we plug k equals 2, this is going to give us cosine of 4 pi over 3 plus I sine 4 pi over 3. And of course you can draw the graphs and find the values of these by yourself. I'm just saving some time because I found these earlier. So this is going to give negative 1/2 minus root 3 over 2i. And then if we try another value of z, k equals 3, we'll find that we're going to have, these are going to cancel, and we're going to have cosine 2 pi plus I sine 2 pi. And we've just cycled back to the first solution of 1. So you're only going to have 3 solutions to a cubic, right? So you should only select 3 values of k, 3 successive values of k, in order to get your solutions. So let's move on now to the exponential forms of complex numbers. Okay, so different day, same video. Now we're on to the Euler's form, or the exponential form of representing a complex number. And it's very similar to the polar form. That's why I've included both of them in the same video, in that we have the angle here and the absolute value of the complex number. And now we denote it as e raised to the I times that angle. So something in the lines of 5 times an angle of, so the absolute value of 5 and the angle of pi over 3 made with the complex plane, the real axis, is going to be in the exponential form something like this, because this is the absolute value and this is the angle. And if we try to put pi into this, we get that e to the I pi is equal to negative 1. And this is Euler's identity, which is e to the I pi plus 1 equals 0. Very famous identity in maths, because it connects the imaginary number pi and e and 1 to give 0. In the end, it all cancels out. So pretty cool. Let's do some fun questions before moving on to an IB style question with the exponential forms. Okay, so if you've ever wondered whether the identity I to the n equals, 1 to the n equals 1 works even with complex numbers, we're going to see, using the exponential form of complex numbers, we're going to see if that works. So I have four numbers here, and we want to work out their value in Cartesian form. And so we're starting with 1 to the I, and then 1 to any complex number, and 2 to the I, and 2 to the z. If you want to give them a go, pause the video and have a go at it, but it's a bit tricky to find the first step, so you might want to pause the video after I do the first one and then try the next ones yourself. So to go about something like this, we need to express 1 to the I as in terms of base e, and the way we can do this is we can say e to the natural log of 1 to the I is equal to 1 to the I. And so this becomes e to the I natural log of 1. And so we have our exponential form complex number where the absolute value is 1 and our angle is the natural log of 1, which is 0. And you can go to the polar form and plug these into the cosine and sine, but we see that I and 0 just cancel out to give e to the 0, and this is just 1. So our identity holds that I to any power, well, let's do this one next, and then we'll see if it holds. So we rewrite this as e to the natural log of 1 to the a plus bi, which becomes e to the a times natural log of 1 times bi natural log of 1. And this just becomes, with the same reason that ln of 1 is 0, this becomes e to the 0 times e to the 0, or 1. So yeah, 1 raised to the anything is 1 even with complex numbers. Okay, so moving on to 2 raised to the imaginary number, we would get same method. So the same method works for all of these examples. We would get e to the natural log of 2 to the I. We can move down that I to give us e to the I natural log of 2. And this will be, now we have to use our polar form because natural log of 2 is not 0. So we would say cosine of natural log of 2 plus I sine of natural log of 2. Okay, so I'll write the values of these in the video. I forgot to work them out beforehand, but the Cartesian values will be displayed in an edit after the video. So now let's work on the next one. So e to the natural log of 2 raised to a plus bi, which becomes e to the a plus bi times the natural log of 2. And this is going to have one component which is real and one component which is imaginary, or complex. Sorry, not entirely imaginary, but complex. So this is going to be e to the a natural log of 2 times e to the bi, so e to the I times b natural log of 2, which is going to be, so now we can think of this, which if we bring up the a into the exponent of 2, it just becomes 2 to the a, right, times e to the I times b ln of 2. And well, we had the same thing up here, except we're missing a b, which we can just multiply the angle of cosine and I sine with. So this becomes 2 to the a, and then cosine of b ln 2 plus I sine b ln 2. Yep, okay. So yeah, those are some pretty fun questions, just to raise real numbers to complex exponents. Now let's go over some IB type questions on the exponential form. Okay, so this is the only question we're going to be doing for the exponential form because I don't want this video to be dragging on too long. But we have this complex number root 3 e to the I pi over 6, and the question is asking us to express z squared and z to the 3 over 2, sorry, in Cartesian form. So z squared is simple enough. We're just going to be squaring this, and that will be 3 e to the 3I pi over 3, right? So in polar coordinates, those are 3 cosine pi over 3 plus 3I sine pi over 3, which will be 3 over 2 plus 3 root 3 over 2I. Okay? And so for raising it to the 3/2, it's a slightly bit more tricky. So we're going to say the root 3 is 3 to the 1/2, and I'm going to keep as it is. Raise this to the 3/2 power. So distributing our power, this is going to give 3 squared times e to the I pi over 4. Right, because you multiply, oh, sorry, this should be a 3 over 4. So you multiply the 3/2 with 1/2, which gives you 3 over 4. You multiply the 3/2 with the pi over 6, which gives you pi over 4. So this is going to be 3 to the 3/4 times, it's going to be sine, I sine of pi over 4 plus cosine of pi over 4, which is 3 to the 3/4 times root 2 over 2 plus there we go. So if you have any suggestions for any future videos, leave them in the comments, and I'll see you on the next one. Okay, very small correction about a question that we previously did, and we were supposed to find the cube root of this complex number, but there's actually 2 more cube roots that I missed, and those arise from the fact that we can add 2 pi k angles to pi over 2 and get the same complex number in polar form. And so basically, when we take the cube roots, we have to consider cases where k is of different values, so integer values. So we have a z to the 1/3 is equal to 2 cosine of pi over 6 plus 2 pi k over 3 plus I sine of pi over 6 plus 2 pi k over 3. And we did actually find one of the roots, which is if k equals 0, then we would get cosine of parentheses should be here. 2 cosine of pi over 6, so 2 times root 3 over 2, which was root 3, plus I sine of pi over 6 times 2, which is I. So we got root 3 plus I, we got that solution. But if we set now k equal to 1, we're going to get, k equals 1, we're going to get the second solution, which is 2 times cosine of pi over 6 plus 2 pi over 3 plus I sine pi over 6. And 2 pi over 3 is the same as 4 pi over 6, right? So it's just, this is just 5 pi over 6 for both of these. And that's going to give cosine of 5 pi over 6 is negative root 3 over 2. Plus I times sine of 5 pi over 6 is still 1/2. And this is going to give negative root 3 plus I as our second solution. So this one was root 3 plus I. And our third solution, the most obvious one, because if we actually find out the values here, cosine of pi over 2 is, cosine of pi over 2 is 0. And this is 1. And so we have 8 times 0 plus I, which is 8I, right? So if you take the cube root of that, you're going to get negative 2I as one of your solutions quite intuitively, right? Because if you raise negative 2i to the third power, you get I to the third power times negative 8, and I to the third power is negative I times negative 8 is 8i. But of course, we can also find that through just plugging k equals 2. Right? So k equals 2, we got z is equal to 2 times cosine of, so this is going to be 2, meaning that's going to be 4, it's going to be 8, 9 over 6 pi, plus, sorry about that, plus I sine of 9 pi over 6. So 9 pi over 6 is the same as saying 3 over 2 pi. And sine of 3 over 2 pi is negative 1. So this is negative I. And cosine of 9 pi over 6 is 0. So we get 2 times 0 minus I, which is negative 2i. So that's just 3. Right there. So I did miss these two solutions, but those are also roots of 8i.